So in this second part of our lecture on bond forces and bond energies in the global section on atomic bonding, I want to make some just general remarks, and I really want to focus in on what kinds of things can we learn about material properties just by looking at the bond curve. Okay, so I've got the picture here that you're looking at. That came from the previous lecture where we were looking at the comparison of a more realistic Leonard-Jones type potential compared to our linear spring approximation potential. But let me remind you a little bit about what we talked about in that previous lecture. We basically showed that a linear spring could be characterized by a potential energy curve in much the same way that an atomic bond can. So let me write that down. Okay, so previous, right, we showed that a linear spring could be characterized by a potential energy curve in the same way as a real atomic bond. Okay, we also we developed a relationship between the potential energy U and the force F in the spring, and we had that as given as follows. So we used a relationship between potential energy U and the force F given by the following. We said that du, the differential, the incremental change in the potential energy, was equal to the negative of the force times dr, which was the incremental change in the bond length. We'll call that here equation 1. Okay, so if you don't remember how we got that, go back to the part 1 and review that. I can rearrange equation 1 to give the following. I can now define force in terms of the potential. Okay, so we can rearrange equation 1 in the following way. We can say that F is equal to now negative du dr. Okay, let's call that equation 2. This is obviously in one dimension where we only have a plus or minus bond distance, right? We either increase the bond length or decrease the bond length. We can write this a little bit more generally. So if in 1D we have a derivative, in 3D we have, hopefully you're thinking we have a gradient, and that would be correct. So we can write the general case for any force with respect to sort of any bond energy can be written as follows. And I'm gonna use vector notation here and say that there's a vector F on the underbar denotes a vector will be equal to negative the gradient of u, and I'm going to put an underbar under the gradient to remind you that it's a vector. Okay, we'll call that equation 3. So that's the general case. And to note here, equation 3 holds for any potential energy. For example, it could just be a chemical bond potential like we have here, but it could be gravitational, and I'll just say etc. Right? Regardless of where the potential energy comes from, this force to the gradient of the potential energy, the spatial gradient that is that relationship holds. So that if we can compute the potential energy and compute how that might change spatially, we can compute the entire force field. Okay? All right. A couple other general things to note. The first is that the equilibrium state of the atoms occurs whenever the potential energy is a minimum. Okay, so whenever the potential energy is a minimum, we get an equilibrium state, and that's going to be, we're going to call the energy at that equilibrium state, we call it U naught, and we'll just say that's equal to the potential energy evaluated at R naught. Okay, we'll call that equation 4. So here's the question that I want to pose. What sort of material properties can we infer just by looking at the potential energy curve? So what can we say about material properties just from looking at the potential energy curve? Okay, so there are 3 properties that we're going to focus on that we can say something about as we look at that curve. Okay, the first one I think is probably the most obvious, and we talked about this last time, but to completely break that bond, we have to give it an energy equal to the magnitude of U naught. Okay? So to completely break the bond requires us to add an energy of the magnitude of U naught. Okay, so what does that mean? Well, that means that materials that have higher magnitudes of U naught are going to be harder to break those bonds apart, and that's going to actually drive up the melting temperature. Okay, so let's say that materials with larger U naught have higher melting temperatures. Okay, so that's one property that we can make some statements about just on the basis of the bond energy curve. Let me show you a table. Okay, so in this table, what you're looking at is different bond types. So here, for ionic bonding, which we'll talk about in an upcoming lecture, you have NaCl, which has a relatively low bonding energy. Then looking at magnesium oxide, which has a higher bonding energy, and you see that the lower bonding energy corresponds to a lower melting temperature, and versus the higher bonding energy, which corresponds to a higher melting temperature. Now, I will point out that that's within the same bond type, right? So if I look at, for example, an ionic bond that has 640 for its potential energy or its bonding energy, compare it to a covalent bond with 450, I see that that doesn't hold. So we need to stay within the same bond type that we begin with. So as we move from ionic to covalent, there's some more complexity besides just the bond energy term. But I just want to point out that there's a correlation, a strong correlation between higher bond energies leading to higher melting temperatures, at least within the same bond classification. Okay, what else can we say? How about modulus? Can we say anything about the modulus? So let's go ahead and consider the elastic modulus. We'll call it E. And I'm going to focus in this case here on the tangent formulation. Right? And all that means is instead of defining the modulus as sigma over epsilon, I'll define it in the tangent form, which is d sigma over d epsilon. Okay? So hopefully that's pretty straightforward. So here we go. There's E, the modulus, and we know that that's going to be equal to d sigma over d epsilon, right? The change in stress over the change in strain should give me my modulus. And what is stress? Well, it's F over A, so I could write this as dF over A, right? But the F that we have used thus far is the force of the bond, not the force being applied. So it actually we have to swap signs, so there's a negative that comes into play here. Okay, divided by the epsilon, and just back to your basic mechanics of materials class, you have delta L over L. Well, delta L is just R minus R naught divided by R naught, right? Okay, A and R naught are going to consider to be constant. So I can write, and I'll pull the negative out and say that's negative then R naught over A times the quantity, let's see, dF. And if I think about what's the differential of R minus R naught when R naught's a constant, well, it's just dr. Okay? Let's call that equation 4. So, but from equation 2 that we wrote above, I can substitute, let's call this equation 5. Sorry, I screwed that up. Okay, but from equation 2 above, I can substitute for F. Right, so remember that equation 2 gave us a relationship between F and the potential energy, right? So I now can write that E is equal to negative R naught over A times d by dr rather, and then now this would be F, but F is now substituted by negative du dr, right? Which I can cancel my negatives out now, and I'm left with R naught over A times d squared u dr squared. Okay? Let's call that equation 6. So what does that tell me? That says that the elastic modulus is proportional to the second derivative of the potential energy curve. Okay? Right, and remember that the second derivative is also related to the curvature of the potential energy. Okay? So we have two features now. Melting temperature and elastic modulus are intrinsically linked to the bond potential energy curve. Okay? One last property I want to focus on is the coefficient of thermal expansion. And sometimes I'll abbreviate that just CTE. Okay? And you know what the coefficient of thermal expansion is, right? And you knew this before you ever became an engineer. If you heat something up, it typically expands. So let's write that in sort of in fancy physics notation. We'll say that the mean atomic spacing increases with increasing temperature. Okay? So heating up something makes it expand, right? So heating up a material makes it expand or causes expansion. Okay, so that's all well and good, but the question I would say is why? Why does heating up a material lead to increase in the mean atomic spacing? So to answer that question, let me try to show you a picture. Okay, so here's a picture that I hope will illustrate why this is. If you note, so if we have an atom that's always at that position, that's the equilibrium, right? But it only resides there all the time in the case of absolute zero temperature. As we increase the energy, of course we know the atoms move, and so they're bouncing around. And as we increase the energy, they bounce around into different regions, right? So let's treat this blue curve as I'll call it the real curve. But what you can see is that because the curve is asymmetric, right? It's steeper as the atomic spacing gets smaller and more shallow as it grows out, that if an atom bounces around at any particular energy level defined by the temperature, on average it spends a little bit more time in this region that's a little bit above R naught, right? So so the feature here is that, so this next value, this would be at some temperature greater than absolute zero, so at T greater than zero, okay? So it's actually the asymmetry in the potential energy curve that gives you thermal expansion, okay? So let's write that down. So the coefficient of thermal expansion, CTE, arises from the asymmetry in the potential energy curve, okay? And what we mean is that at higher temperatures, the atom on average, remember the atom's always moving, at higher temperature, the atom spends on average more time at some larger value of R than R naught, okay? So at higher energies, right, which corresponds to higher temperatures, an atom spends more time at some R greater than R naught, okay? Or just remember, the atoms are always moving, so it's always about where their average position is. Okay, in addition, one other thing to note about the CTE is that the CTE is going to go up as the magnitude of U naught goes down, okay? So as the magnitude of U naught, right, so that's the depth of how deep this energy well is, right? As the magnitude goes down, which means that we have a shallower well, the CTE goes up, right? And you can kind of see that. If I had a well that went clear down to the bottom of this page, right, it's very steep, so increasing the energy isn't going to change the atomic spacing very much, which means the CTE would go down. If, on the other hand, if my curve didn't even go as deep as this zero value, let's say it went down to only 0.2 and came out, then if I raise any energy at all, I'm going to oscillate a lot, and I'm going to end up with even higher CTEs, okay? So those are the three properties that you can make some statements about just by looking at the potential energy curve. I want to make some final comments now about potential energy curves of bonds. Okay, so everything we've talked about so far has been all about bond stretching. So far, we've only talked about bond stretching. Okay? But other forms of bond potential energies can exist. For example, we could have a bond angle change, right? Bond angle bending if you want. I'll just say change. You could have bond torsion. You could have other long-range effects from bonding with far field atoms. Okay? When you have these, the total potential energy of an atom is what matters, and it's going to be the sum of all these other potential energies. Okay? So in this case, we say that the total potential energy of an atom would be the sum of all of these. So we would write then that U is equal to U stretch, which is all we focused on in sort of this discussion. But then we would add to it maybe U of bond bending plus the potential energy due to bond torsion plus some other long range terms. Okay, so the bond potential is actually fairly complicated, and in many cases, in most cases, in fact, you can't write it as simply a function of r. It's going to be a function of maybe r as a vector. You need the directional component. So I'll just mention kind of in closing that the calculation of bond energies is not trivial. And in part, that's because of the complexities of the orbitals. Okay, so what I mean by that is that I think we're used to thinking of orbitals in like the Bohr model. So let me just give you an example. Here's the Bohr model. Right, and you're used to thinking of atoms, I think, in terms of this Bohr model, where you have some nucleus here at the center, surrounded by these nice concentric rings of electron shells that you learned in your chemistry class. Okay, but in the real world, that's not how bond orbitals or electron orbitals look. So here is the real case. Okay, so in the real case, what you see is that you don't have some sort of spherical orbitals. You have very complex orbital shapes, and they change even depending on which level of shell you're in. So one atom may have sort of a combination of all kinds of different orbital shapes that give the definition of the potential energy a lot of complexity and directionality. So even though we're using the potential energy to say things about material properties, just drawing a picture of that potential energy is far from a trivial thing. Okay, but the reason that I mentioned mention this is because if something is dependent on the bond energy, like let's say elastic modulus, it suggests that unless you actually change the bond itself, you won't change the modulus very much. So all the heat treating that you want to do to a steel and the cold working that you might want to do to make it stronger, which we'll talk about in this class, all of those efforts, they can do things to change the strength, but you'll never change the modulus. And the reason that that is the case is because in all of those things, you're not actually changing the atomic bonds themselves. You're just changing the arrangement of groups of atoms, but the bonding remains the same. So understanding these concepts give us a little bit of a clue into the kind of properties that we can change with processing and the kind that are essentially set by the materials that we choose in the first place.